Hello, physics students. One more video, last one for Chapter 9, solutions for these problems. This is some review before we head into our test, including going back and making sure we know how to find center of mass and that we haven't forgotten about impulse. All right, let's see, 85. The speed de-amplifier. So we've got blocks colliding. 1, 2, and then 3. They have masses of m1, 2m1, and 4m1. Right, the masses double each time. Alright, so what do we have? This one starts off with a velocity of 4 meters per second. The other two are stationary. Alright, so first thing that happens, it undergoes a one-dimensional elastic collision. Elastic collision, that means that both momentum and kinetic energy are conserved. And that means we're going to have that extra system of equations thing to do. That's a pain, but oh well. And then next, block 2 undergoes a one-dimensional elastic collision again, so we're going to have to do it twice. And then we want to know what the speed of block 3 is. So let's get started. So in the first collision, momentum is conserved. So what do we have beforehand? We have the mass times velocity of the first one is equal to, the first one is going to have velocity, it's bouncing off that one, I don't know what it is, plus 2m1 times the velocity of that second block. And our m1s cancel out, so I end up with 4 is equal to v1 plus 2v2. But since it's elastic, I know that the kinetic energy is also conserved. So what does that get us? 1/2 m1 times 4 squared is equal to 1/2 m1 times its velocity squared after the collision, plus 1/2 2m1 times its velocity after the collision. Let's go ahead and cancel out the 1/2 m1s. So I end up with 16 is equal to v1 squared plus 2 v2 squared. And I'm interested in eventually finding the velocity of that block, so I need to find v2. I could find both, of course, because it's a system of equations. But I'm going to substitute out here, so 16 is equal to 4 minus 2v2 squared plus 2v2 squared. I'm doing something called algebra here. You've heard of it, I'm sure. Of course, they don't teach that anymore at Riverheads High School. I heard that it comes from the bad parts of the world. So V2 be equal to 16 over 6, which is 8 over 3, which is about 2.7 meters per second. Right. Now we get to do that whole thing again. So now this block is going to crash into this block. Maybe I should have left that as 8/3. I don't know if that'll be any better. So doing it again. momentum before this collision. I'm ignoring the first block now. This is the collision of this block and this block. So I have 2m1 times its velocity of 8/3. We'll try it with the exact values and see how that goes. And then afterwards, I have 2m1 times the velocity of block 2 plus 4m1 times the velocity of block 3. And the m1s cancel out, and I get 16/3 is equal to 2v2 plus 4v3. Kinetic energy also conserved. In my experience, the College Board sure is keen on making sure that you know that when they say a collision's elastic, that you immediately recognize that that means kinetic energy is also conserved. So it's important to know, not because the College Board says so, of course, but it's a thing. m1 times velocity squared is equal to, am I going to run out? Let's see. Slide that over so you can see everything here. And then afterwards I have 1/2 2m1 times its velocity. I'm going to call this v2 now, right, because that's what I called it here, not to be confused with this v2. Sorry if that's confusing. That's the one before the collision, and I'm now finding after. Squared plus 1/2 4m1 times v3 squared. All right, let's cancel out the 1/2s. Let's cancel out the 2m1, which we'll leave here at 2. So then I have 8/3 squared, which is 64/9, is equal to v2 squared plus 2 v3 squared. All right, beautiful. And let's go ahead and divide this one by 2 and solve for v2. So v2 is going to be equal to 2v3 minus 8/3. Just make sure that that's right. v2, no it's not, it's backwards. 8/3 minus 2v3. All right, I divided that by 2 and then subtracted that over there. Okay, so 64/9 is equal to v2 squared plus 2 v3 squared. And I think there's going to be a payoff here, right, for keeping that, because that squared, you notice this is happening every time that those numbers cancel out. Minus it's 16, so 2 of those. Doing some algebra here again. I think that looks okay. So those cancel, and I get 6v3 squared minus 32/3 v3. So my answer is going to be 32/3 divided by 6. 1.78. So that's a lot of algebra to get there. And let's just check and see if we did that. Right, we did. Yay. All right, now B. What's the speed, kinetic energy, and momentum? Are they greater than, less than, or the same as the initial values for block 1? So the speed is less, right? That's the speed here. Speed of the first one was 4. Right? Part B, C. The kinetic energy. Well, the kinetic energy of block 1 before the collision is 1/2 m1 times squared. That's 8 m1 joules. And then the kinetic energy of block 3 after is 1/2 times 4 m1 times 1.78 squared. That's 2 times 1.78 squared. That's 6.33. So, again, it's less. And since all these, that shouldn't be surprising because these are elastic collisions, so the total kinetic energy is going to be the same. And since the first two blocks are still moving after these collisions, the third block can't have all the kinetic energy, right? It can only have part of it. So it does have part of it, it has most of it, but not all of it. It certainly can't have more unless there's a explosion or something. All right, and then D, the momentum of block 3. And then same difference, it's got to be less than, right? We know that it has to be less. Oh, actually, we don't know that because they're moving in different directions, right? So if these ones bounced off, which they would, this would bounce off that way because this is a bigger block, likewise. So we better check that. So let's see, momentum of the first block before is equal to its mass times its velocity. And the momentum of the third block after is 4 m1s times its velocity. Yeah, and you can see that that's definitely going to be more. And how is that possible? Did we gain momentum? No, it's because the other ones have negative momentum, right? So the total momentum will still be equal to this. And we could find a number on that just for the sake of completeness here. So about 7.12. So that's greater. All right. That's a lot of work, a lot of algebra to do there. Good practice. Now, number 89. All right. We have a 1,400 kilogram car moving at 5.3 meters per second. It's initially traveling north. And after completing a 90-degree right turn in 4.6 seconds, so it's now going this way, the inattentive operator drives into a tree, which stops the car in 0.35 seconds. In unit vector notation, what's the impulse on the car due to the turn and due to the collision? And I suppose we're supposed to presume that the speed, as the driver makes the turn, that the speed of the car does not change. I don't see anything to indicate otherwise. So I'm going to go ahead and operate under that assumption. So impulse is equal to change in momentum. So let's see, the impulse, that would be equal to the final momentum minus the initial momentum. Of course, these are vectors here, right? So I'm going to call this would be the positive j direction. This is the positive I direction. So the final momentum is the mass times the velocity, and final, it's in the I direction, minus the initial, which is the same value, but in the positive j direction. And what did they want to know? They want to know, in unit vector notation, what's the impulse on the car. So that's it. I just have to multiply that out. So what is 1400 times 5.3? So it's, 74, 20 I minus 74, 20 J kilogram meters per second, or Newton seconds if you want. And which number is this? This is 89. Let's check. Yeah, and that is correct for that part. Good. That was part A. Part B, they want to know what is the impulse on the car due to the collision. So start from the same place. So you have here j is equal to final minus initial. Now, of course, it crashed into a tree and stopped, so the final momentum is 0. So that's negative momentum initial. And now initial is this, right? Because we're crashing into the tree. So the initial momentum is now 1400 times 5.3 in the I direction. So it's just that. Part C. What is the magnitude of the average force that acts on the car during the turn and during the collision? So here we're going to recognize also that J impulse is equal to the integral of force with respect to time. But if we know, if we're just talking about average force, and we know also from calculus, we know average value of a function, that this is also true. And they gave us the time interval, so this is what we're going to use here. So the magnitude of the average force, they want to know magnitudes, so I can use my answers from here. I'm going to go ahead and find here the magnitude of this. I just have to Pythagorize those. So that's the square, it's just the square root of 2 times this, right? It's an isosceles right triangle. 420. So about 10,500 is this. That's the magnitude. And then the time interval is 0.35 seconds. So divide by 0.35 seconds. It's about 30,000 newtons. Or 30 kilonewtons, if you like, that sort of thing. And that is not agreeing with the book. I don't like that. Let me just pause for a second and see if I can figure out what I did wrong there. Let's see. During the turn. So this is the change in momentum. Right? And I have the magnitude of that. And then I divide it by the 0.35. I don't see anything right off the bat that I feel like I did wrong there. During the turn. Well, I think I have to stick with my answer there. I don't see anything that I did wrong. If you found something, then I'm sure you'll let me know, and maybe you can post it in the comments. But I don't see anything wrong there. We're kind of in the right order of magnitude. I suppose the book could possibly have made a mistake. Anyway, let's not dwell on that. That's the right idea for sure. And then D, we'll see if we can get the right answer here. We have same idea, but now we want the magnitude of the average force because of the collision. So that is, so the, let's see, that just has a magnitude of that, right? During the collision, oh, sorry, because the turn, I used the wrong time. I see what I did now. If you go back and look at the problem, the time that it took to make the turn was 4.6 seconds. That's what I did. So sorry. So here we're going to have 10,500 divided by 4.6, and that's about 2,300. So sorry, that's what I did wrong. I used the wrong time. 2,300 newtons. And I think that's in agreement with their answer there. Yes, it is. All right. And then, so here, now we have the change in momentum here. And that's happening this time in, that's the time, the 35 hundredths of a second. So, magnitude of that. And I'm just doing magnitudes here, so I should have lost that negative sign, right? Magnitude is 7420 divided by 0.35, and that's about 21,200 newtons. So that's bigger, a lot bigger. Okay, and then last they want in part E, what's the direction of the average force during the turn? Well, if you look at this equation, the direction of the average force, if you're thinking about directions, this has a direction, and this has a direction, and they must be the same direction, right? So what is the direction of the impulse? Actually, is it the turn or the crash? During the turn. So the direction here is positive I, negative j, same number. So positive I, negative j, same number, so the direction here is 45 degrees. And this was a north, south, east, west, so I could say south of east. Or you could say negative 45 degrees. That would make sense too, right? All right. All fixed up. Let's see, 101. Here we have this reminds me a little bit of one of your physics so far problems, although this one I think is a little easier. Two blocks, one stationary, one sliding this way, and this one, they're going to stick together and come off and land somewhere. So let's see, 3.2 kilogram box. This is 3.2. It's going to collide with a 2 kilogram box of ballet slippers. Those are lighter than running shoes. Although the running shoes now, these days, those sort of barefoot shoes, pretty light. Might have to revise this problem. The height of the table is 0.4 meters. And the speed of this one is 3 meters per second before the collision. And they stick together. And we want to know what's the kinetic energy just before they strike the floor. Let's find the velocity. So at this collision, initial momentum is going to be equal to final momentum. Initial momentum is just the 3.2 mass times the velocity of 3. Afterwards, they stick together for a total, that's a 2, total mass of 5.2 with that velocity. So let's see what we have there. 3.2 times 3 divided by 5.2, about 1.85. And they would like to know what is the kinetic energy just before they strike the floor. Well, that's an energy problem here, so if we wanted to make energy pies here, we would have kinetic energy, but we're also off the ground, so we'd have gravitational potential without much worth. And then when they hit the ground, they're at the ground, so it'd be all kinetic. So let's set that up. So we have initial kinetic energy plus the gravitational potential energy would be equal to the final kinetic energy. Right, it's equating those pies. That's 1/2 m. They're stuck together now. That's the whole thing. V squared. Just found that. Plus m g h is equal to 1/2 m v. Oh, I don't even want to know this, do I? I just want to know what the final kinetic energy is. I don't need to know the final velocity. So that's just equal to the final kinetic energy. That's what they want me to solve for. You could solve for v and then plug it back in, but that would be unnecessary. All right, so let's just crank that out and then we're done. So 1/2 m v squared plus m g h. It's about 29 joules. So a nice little bit of energy work in the energy work. Nice little energy reminder, review, whatever you want to call it there. And last problem, and a center of mass situation here. What are we doing now? This is number 114. See if I can squeeze it in here. So we have this. This looks like a lot like one of those first problems that I showed you. I'm just going to scale this out to 3s when we first did center of mass. Do you remember those formulas? They're very intuitive, right? It's just all about the weighted average. So we had a piece cut out of this thing. There's more than one way to dice this thing up into nice shapes. However you do it, I don't know how you do it. I'm going to do it this way. You can do it your way. I'm going to divide it up into those 3 pieces. And this is the center of this one, right? This is 4 units across, 6 up and down. This is the center of this one, and this is the center of this one. So this problem reduces to basically finding the center of mass of 3 particles, although the 3 particles do not all have the same mass. Since this thing is a uniform square plate, I'm just going to count up the little squares and basically weight them by the area, right? So this has an area of 4, this has an area of 4, and this one has an area of 6 by 4 of 24. Right? So the x-coordinate of the center of mass. If you struggled with this one, didn't remember, I think at this point you might want to pause and see if you can set up these equations. That'd be a good idea. So 1/my total mass, which is 32, units. And then here's my weighted average. Mass, I'll put the positions first. So let's call this one, I'll do 1, 2, 3, like that. So the first particle, the x-coordinate is -1 times the mass. The second particle is an x-coordinate of 2, has a mass of 4. And the third one has an x-coordinate also of 2 and a mass of 4. And that's -24 plus 16, that's -8, so that's -1/4. And did they give us units here? Are these like meters? What's D? D is 1 meter. Right? 60 equals 6 meters, so D is 1 meter. So -0.25 meters. That is the x-coordinate, the center of mass, which is part A. Part B, the y-coordinate of the center of mass. Same thing, weighted average, except now I need the y-coordinates. The y-coordinate of the first one is conveniently 0. Y-coordinate of the second one is 2. And of the next one is -2. That's 8 minus 8, so that's 0. And looking back at this shape, we really could have said that, I think, without doing any math. This thing is symmetric with respect to the y-axis, which means that the center of mass has to lie on this line of y-coordinate 0, because it's a line of symmetry of the whole shape. So no big surprise there. And if you just recognized that and threw down the 0, I think that's probably okay. Good for you. And that's all.